So, good morning, everybody. So, you are now at the course Quantitative Big Imaging, and I'm Anders Kestner, going to give this course. It's actually pretty many people enrolled on the course, so we'll see if everybody would come. That would be pretty crowded in here. Also, how is my voice? Can you back there hear me? Is it okay? Great. So, just to check, we have got some complaints about this room that is sometimes the voice is not reaching the people in the back of the room, so just to make sure. So, today I'm going to talk about a little bit of the course overview and also a little introduction to images. I recognize some people from the micro nanotomography course. Some slides you may recognize, but most I think is new. So anyway, I think you can enjoy the course. In general, there's a lot of new stuff, so it's no big overlap actually. So today, first a little bit knowing who we are. The people giving the lectures and helping you, and who you are, and what you can expect from the course, and why at all the course exists. It's a mixed course, putting in a lot of material, but there is a motivation for it actually. So, and probably you have seen this motivation because you're here. So, in the overview, I'm going to talk about what is an image at all. And where do they come from? Also, the topic about science and reproducibility, how important it is and what it is. And then I'm rounding up today's lecture with the workflows, how to work with images. So first of all, me, I'm a beamline scientist at Paul Scherrer Institute. Normally I'm counting neutrons, making images with them. And I'm working at a cold neutron beamline icon. Also giving some lectures here at ETH. Before that, I worked as algorithm developer at Varian Medical Systems in Baden-Württemberg. And, well, going back in time, did a postdoc here at ETH at Institute for Terrestrial Ecology. I think they changed name by now, but anyway. That was also my port into working with imaging. I came with the luggage that I studied image processing and signal processing at the Chalmers Institute of Technology in Sweden. And then as postdoc, I started analyzing images mainly of soil samples. It's not only me around here. We also have Stefano van Gogh. And he will help you, and also I will help you with the exercises, and also if you decide to do a project, also these. And he is a PhD student in the X-ray microscopy group here at the ETH and also at the Swiss Light Source at Paul Scherrer Institute. And then I'm right now negotiating with Kevin Marder, who actually started this course and developed it. So I'm actually giving this course for the first time this year. Right now he is a data scientist at Apple. Before that he worked with image analysis and machine learning for different data sets. But he also has a history as a PhD student at ETH and at Swiss Light Source. So we still need to confirm with Apple that he is allowed to give a lecture. But I hope that will work out. So how are you? There is a wide spectrum. I looked at the list and you come from very diverse places. So we have biomedical engineers, we have physicists, chemists. I also saw a statistician, mechanical engineer, computer scientist. So it's really a great variation of people coming here to this course. And also the skills you bring in when you come to this course is very different. Some are on the level, well, I have heard of Python, which is a programming language that we are going to use a lot. And then there are some people that write template C++ code and do heavy-duty optimization. I don't know if it applies to you, but that would be the variation of people and the background knowledge that we can expect. So that will be a challenge, but I will try to guide you through the exercises, and also these slides that you see here. They are actually Python notebooks. So if you go on the web page, I hope you got the mail yesterday with a link to all the material. There you can see all the Python notebook, and if you want, you can look into how some of these slides were produced, and then you can get some ideas also how to work with the material. So actually I'm already talking about this. These Python notebooks, they help you. So I'm doing it stepwise in a way that there is some introduction text, maybe some example, and then you can try doing your own examples and trying different parameters in the exercises. And actually today's exercise is more getting you a little bit up and running with Python. And the important thing is you know the concepts, how to work with the material, and getting a toolbox that you really can use in your work, in your master thesis or in your PhD project. So you really have a good toolbox afterwards. Usually we have one exercise per lecture. They are optional, but actually pretty good to do if you want to understand what's going on or get a little bit hands-on feeling on the exercise, on the things I'm talking about. Previous years there was a lot of work using a tool set called KNIME, which is a graphical user interface where you drag and drop boxes. You're free to use that. I'm keeping that material still in the exercise list, but the main material will be in Python. And actually the MATLAB scripts, that's an old thing actually. That's obsolete. Then there is a science project. This is an optional project where you can take a piece of your master thesis or your PhD project and work on that, and we will guide you. And in the end of the course, we will have some presentations where you can see what you have, where you can present what you have achieved. Say 10 minutes presentations. So so it's optional. It's a little bit more work, but I hope it will help you, and also that many of you decide to do it, because that will enrich your experiences from this course. Literature, well, in image processing there are loads of books. But anyway, some that I can recommend, in particular the one by John Ross here. It's an overview book of essentially the main things you can do with image processing, traditional image processing today. Joachim Weikert, he does a little bit more advanced stuff, working with tensor fields. But I would say, as a starting point, you have a good reference in John Ross' book. I think it's over 1,000 pages, so it's a pretty heavy thing. But it's online. You can download it from Springer, from the ETH library, and I recommend you actually to do it. Today, I'm going to talk about the imaging part. And as you can see here in the lecture notes, there's a lot of links. I'm not going to exactly tell everything that are on these links. For example, the first one is a slideshow of about 40 pages. And there's no time to actually talk about that. But the main essence is that it's important to have a good tool to make reproducible workflows. And very important today is open data, open science, open source. Everything should be open. Many fund givers, they require actually that you have open publications, and many journals, they even ask you to publish your data open and also your workflow, so it's possible to reproduce what you have done. So it's important to take this into account. And with that, we also come to the thing about reproducibility, that you should be able to reproduce what you have done in your experiment. So it's not like, oh, now I'm testing this and clicking around and, oh, wow, yes, I got the right thing. What you need to have is more or less a documented workflow. I usually recommend to have a script of some kind that goes step by step through the workflow, and then you have a database of parameters that you have tested using this workflow. And with that, you can always reproduce what you have done. And that's also important if you write a publication and the reviewers say, this is not good, and you have to redo the work in some parts and redo plots. Then it's good to have efficient workflows to reproduce what you have done. And that is in principle what is said around in these pages that are referenced here. By the way, this Trouble in the Lab is an article in The Economist, but you can register for a free access to that to that article if you provide your email address, and then you get a lot of mail afterwards. They tell you, oh, now we have this nice article, etc., etc. But anyway, the article is actually worth reading. So, coming to the motivation, why are you here? You got data. Starting first, you maybe submitted your proposal, yay, it got accepted, you got 2-3 days of beam time, and you come to the beamline, happily placing your sample there, and then you start acquire data, a lot of data, sometimes terabytes of data, and then you come home, you wake up, and yuck, I have to do something with it. How should I do it? I have nice images, okay, they look great, but can I really get some real information out of it? And that is what we are going to talk about here in this course. So, for example, you come up with some nice data. The data is acquired, reconstructed, and then you do some nice workflow, doing fancy stuff, doing magic stuff, do some math on the top of it, and then you do something that's complicated, and well, in the end, you come up with some conclusion. In this case, ice cream is good for bones. Well, that's maybe not the one that we are going to talk about, but anyway, that could be a conclusion. But anyway, to get the whole workflow through how to get from you have your sample prepared, actually that's a lot of work in advance usually, that you prepare your samples using your own project. But it's not only that, it's actually to prepare the sample that is suitable for the imaging experiment. I usually say that it's needed about 2-3 beam times until a user really gets the kind of experiment to get the answers they want. In the beginning, it's more or less just testing, trying, maybe it's even a test beam time. But to really get the real answers under the conditions you want them, that takes time and experience. For some groups, they already know, okay, we have this kind of sample, we build this kind of container, and everything is great first time. But that's not usually the case for the first-time users. And then we come to the point, okay, one sample is nice, but mostly you need statistics. So we have to do several replicates. Repeat the experiment on different conditions, different or maybe groups, same sample, same condition, and then several groups of that, and they produce a lot of images. Depending on beamline capacity, it's maybe 10, and you're happy when you get 10. And on other conditions, you may get thousands of images, but you don't want to do the manual work, clicking through the same workflow again and again and again 1,000 times. So you have to do something that automatizes it and let the computer do the main work. So actually the thing about producing a lot of data is that today's detector, they're pretty fast. You can do acquisitions at Tomcat. This example says 1,500 times a second. That's 8 gigabytes per second. And that's more information from that they produce on Facebook per day. And even 3 times as many images per second that is uploaded at Instagram. So it's a huge amount of data that is produced from these systems. And with the different image sources, you produce images in different speeds. You have the fast acquisition at the synchrotrons. Also, the nanoscope, it's extreme. Wow, 10 terabytes per day. And that's fantastic amounts of data. And then you can do a little small one. Then you do go hiking or go snowboarding, put on your GoPro camera. That produces 60 megabytes per second. And that gives you a little bit a scale of what the difference is. So there are different things to think about when you set up the whole experiment. First of all, as I said, the whole experiment design, making sure that you have the right conditions and that the experiment is efficient when you do it. And then you maybe remember this pile of hard drives. That's no way of organizing data in a secure way. So you have to make sure that you can do backupping, you can organize the data in a way that is accessible, not naming the files in weird ways that makes it just strange to access afterwards. So you have to think about how you organize the data in a way that is easy to analyze, but also easy to understand. So you have to have a balance between them, because if you start just putting index numbers of everything, it's hard to get into it, and you have to have some kind of translation table afterwards. And then we have the measurements, where acquisition speed is steadily increasing all the time. And of course, we have finally, once we have the data, the post-processing part. So we have to usually first, if we do tomography experiments, reconstruct the data. Then we have some volumes, but what to do with these volumes? And typically, over the years, this share of how much time is spent on what has changed over the years. And in the beginning, there was a lot of time spent on experiments. And the post-processing was almost nothing. But, no, not almost, but it's like a third here. Now, today, we are coming towards that the acquisition almost takes no time at all. But the complexity of the data makes it a large, really large fraction for data management and post-processing. So all this has changed over the time. And many, when they start doing these imaging experiments, they don't realize that actually the processing is the major part of the experiment. And that also puts delays. There are a lot of statistics about it, that unsupported users, they need about 2 years to produce a publication. Under other conditions, when there is a close collaboration with experts, then this time is reduced maybe to a year. So there is a great possibility to improve the time from experiment to publication by putting the right efforts into the post-processing. So, how much is a terabyte actually? Well, you know you can buy a terabyte hard drive, but if you look at images, let's see if it works. No? Yeah, so images like this, this is a 1000 by 1000 image. So it's 1 megabyte, or if you take it 16-bit, then it's 2 megabyte. And if you look at that every second, how long would it take you? Now let's see if this one works. Oh. No, it didn't work. And then I have to go back. No, there it is. Okay. So, in the end, it would actually take you 138 hours to watch a terabyte if you watch 1 image per second. Well, you can also see it like a normal Blu-ray. I think it's 8 or 16 gigabytes or something like that. So it would be pretty much movie time also. Now, thinking about this, that it takes 138 hours to look at an image 1 second. And 1 second to look at an image is not enough to tell something about it. You can get a first glimpse, you can maybe give a quick statement about it, but you can't do any kind of analysis. So, if we have an image here representing some bones, a piece of a bone, and there is some pieces here that you want to look at. And you should also ignore the large one, because they are artifacts or something that was segmented the wrong way. So, but anyway, in 1 second, how much can you tell about this image? I would say not very much. So we need some kind of analysis and to get this right. So now, you do this not only for one single slice, but you do it for a volume, and all of a sudden you have 96 samples. It's getting a bit tough to do it. So then we really need the computers and some kind of automatic routines to do this analysis. And well, to make it really painful, first of all, experimentally, producing over 1,000 samples takes, first of all, a while in the lab, and you may even need to introduce some lab infrastructure. In this case, I think it was even done with a robotic arm that put the samples in and out during the experiment. And now is the question, with all these that are actually needed to get the biological, to cover the biological diversity in the data, how do you now start putting numbers on it? Because in the end, you want not to have nice images. Okay, they are great to look at, something that spins, but I think you get tired of it after a few of them. What you really want are graphs telling something about the morphology of, for example, cells or cracks, or what happens on different pieces in the bone. And this is the information we want to have. And so we want to get graphs out of all these data. And then is the question also, some things you can put really exact numbers on, but other things, they are a little bit softer. So if you ask, are these features here in this image, are they aligned? On the left one, we say, well, kind of aligned. The middle ones, they're pretty straight, so they're well aligned. And then in the end, not really aligned, or possibly, or are they? That's the question. So then you have to have some kind of way of measuring these soft metrics. Let's see if this one runs, which I don't think. So let's play it like this. So we have this movie, which is a foam, where there are bubbles that are rising. And now we want to quantify something about these bubbles. First of all, how many bubbles do we have? How fast are they moving? Are all moving at the same speed? Which is the speed? Is it depending on the size? Is location important for the movement? And questions like this is information we want to extract from the images. And now we are actually talking about 4-dimensional information. So we have 3 spatial dimensions plus the time. And now we want to make conclusions about that. So this was a little bit overview of questions that can arise. And looking at the course, we have this list. And actually, on the web page, if you go on, no, not that one, let's see. On the web page that I sent you yesterday, if you go down a little bit, you actually have the weekly lecture plan. And there you can see, first of all, you can have all the slides, you have the exercises, and here you can download the material also. And if you want to download the whole material, then you can go to GitHub, either get everything as a zip file, or you can also clone, if you are working with Git, then you can also clone the repository, then it's easier to update also if you want to do that. By the way, how many are working with Git already? Few. Good. Good. Actually a great way of keeping track of what you're doing. So if you're into writing code in some sense, it's good to use a version control system. That makes it possible to see the development of the code, and also if something goes wrong, you can easily go back and get to a safe condition. Right now, I've only prepared the lectures until the 5th of March, but that will evolve over time. And you have this separator here that marks where I have the material for this year and the previous material. I'm also recording the videos. This is still the lecture from last year, and it's on YouTube. I have to see where I upload it, but it will be YouTube, but the question is in which channel. So also if you would miss one lecture, you can listen to what I said before. Well, so much about the overview. Actually, this one needs to be updated because I have image enhancement next week instead of in 2 weeks. So there are different topics. Segmentation is one. How to convert these gray level images that you have into some structures or few classes. How to identify structures when there is noise. Noise is always a mess when you work with signals. So how to handle that. Then we have the analysis, looking at the shape or characterizing objects in the data, and maybe do some counting on numbers, dimensions, etc. Then we come to the big imaging topic, actually the case when you have a lot of data, how you do the management, how you do the processing, and how to get statistics out of the data in that way. And this is also where I hope that we will have Kevin to speak. And then we come to the wrap-up, which is actually presentations of the projects that you hopefully decide to do. So, with that, I'm actually would say we take a little break here because it's a natural place here, and then we continue after a break on working on what are images.